My name is Joseph Miller,
And my name's Kenny.
and today we're presenting on a paper by Zhou et al. On IO-aware performance analysis, modeling, and optimization. IO used to play a heavy role in software utilities such as Hadoop MapReduce, but with the movement to newer types of frameworks like Apache Spark, IO is no longer the major bottleneck, but Spark clusters using SSDs were found to be 10x better than hard disk drives for certain stages of large scale genome processing. And this led the research group to want to investigate further into this to see what kind of impact IO operations have on Apache Spark based applications, um, given that IO is no longer a major bottleneck for these types of applications. So a bit of background on what Hadoop MapReduce is. As said before, it was bottlenecked by IO operations. It was about 100x slower than Apache Spark due to Spark's in-memory compute clusters that it uses to do its computations. And it saw about up to a 70% increase in performance with SSDs versus HDDs. And because a lot of these previous, frameworks that existed had such a major improvement by swapping over from hard disk to solid state, led to the research team thinking, maybe we can get a bit more cost per performance using SSDs with Apache Spark, even if it isn't the most impactful metric that you can use for optimization. And MapReduce used to work by essentially splitting your large set of inputs into a bunch of different maps, and then it would perform a shuffling process a shuffle and then reduce type process where it would figure out how many duplicate inputs you would have had on your set and then reduce those inputs down to cut on your data size. And then Apache Spark came around, which is a unified analytics engine for large-scale data processing. It utilizes fault-tolerant, resilient, distributed data sets that are cached in memory. And it also utilizes distributed file systems like HDFS that allows for parallel processing of large amounts of data, such as stuff through like SQL, or the main application that they focused on in this paper, the Genome Analysis Toolkit, which allows for large-scale data processing on computational genomics. It basically has three major stages that were looked at in this paper: mark duplication, base recalibrator, and save as new API Hadoop file. Essentially, what these major three stages do is mark duplicate, it groups together reads from your BAM input file, which contains small DNA fragments that you'd get from the DNA sequencing machine. And it finds all the alignment information and marks what are duplicate reads. That is then passed into the base recalibrator stage, which builds a statistical model on how to update the quality scores of all of the aligned reads. And then all of this information is passed into the third stage, save as new API Hadoop file, which updates the quality scores of all those, and then saves that as an analysis ready file as a BAM output. So SSD versus HDDs for cloud storage. Essentially what we have here is cloud providers like Google will offer different costs for different IO resources that they offer. SSDs are higher bandwidth, but of course are more expensive to produce per gigabyte. So there's a trade-off between cost and the cost per performance. And building an IO-aware analytical model will allow users to optimally tailor their cloud computing resources based on cost per performance.
And so what they found was that changing the I/O does have an impact on the runtime speed of each stage, but the stages respond differently to this change in I/O speed. So one thing they observed was that one form of storage is more sensitive to I/O than the other. So for example, as you can see in the chart on the bottom right, swapping the local directory from a hard drive to an SSD has significantly more improvements than swapping the file system from a hard drive to an SSD. We found that the biggest takeaways from this information is that each stage of the workload responds differently to I/O speed improvements, and it isn't just a clear-cut, uniform, linear relation where if you increase the I/O speed, you'll get a linear increase in performance. That's just not how it works in this test bench. After looking at the I/O alone, they also looked into how the number of CPU cores impact the runtime. They found that the number of cores does generally improve the runtime as long as the I/O is not a bottleneck. So this is shown in the data in the bottom right, where the system with SSDs has both the file system and caching times decrease, or the runtimes decrease as the number of cores increase. On the other hand, though, the systems with only hard drives don't see this improvement in runtime. And this is most likely because of the bandwidth contention that you face when you're using slower I/O. Multiple cores are going to start competing for that I/O bandwidth, and it prevents much parallelism. Yeah. And so the group wanted to take a closer look into this to figure out what exactly is causing this, these different levels of sensitivities and what's causing the varying runtimes at an operation level. And so they decided that one factor is the I/O intensiveness of each operation. So for example, there are shuffle type operations that require more I/O transfers than the standard read or write instructions. And along with that, there are larger RDD operations that can't fully fit inside of the cache, so they'll be required to have more back and forth interactions with the memory. So in those cases, these type of operations will have different levels of I/O intensities. Another factor is that each operation has an effective I/O bandwidth that is dependent on the size of their data requests and also the I/O speed. The best example of this goes back to the example earlier where the hard drives result in a lot of contention. A more specific example is in the case with the shuffle read operations. Those operations are more likely to have frequent but smaller data exchanges. So because of this and the larger latency associated with hard drives, their effective bandwidth is lower than compared to running a shuffle read operation on an SSD, where the latency for having multiple transactions is much smaller, and therefore you receive a higher effective bandwidth. So putting all of these factors together, the group created a model that predicts the timing of each stage, that takes into the different data request sizes, the CPU cores, and all of the execution and I/O overlap times. They created a model that uses the max function of tscale, treadlimit, and twritelimit. So to go further into what that is, tscale is the execution time you would expect for a certain stage in the case where neither the read or write I/O operations are a bottleneck, and it's largely dependent on the compute time and the number of processors. On the other hand, treadlimit and twritelimit are the execution times when the respective operation is bottlenecked in that stage. So with this timing model, they predict that the time for each stage will be the maximum of either the non-bottlenecked time or the times when either read or write are bottlenecking the performance. Okay, so to test the accuracy of their model, the group compared their predicted runtimes for the GATK4 tests against the actual measured results that they got from running it on a real system. What they found was that across all of their tests, the average error is less than 6%. And so far, all of their data and all of their analysis has been based off of the GATK4 test bench, but they also wanted to show how their model's accuracy compares to the predicted runtimes of other big data applications that aren't just GATK4. And so to demonstrate that, that their model isn't entirely dependent on Spark Bench, they're also using other applications that are hosted on another bench called Big Data Bench, and they compare their accuracies in the same way as before. So for different algorithms, such as logistic regression, support vector machines, PageRank, triangle count, and TerraSort, they found that the maximum average error rate across all of those tests is 8.4%. So through this, they claim that their model can predict the runtime of different workloads in different frameworks as well, given the so long as they're given the necessary system and behavioral specs that they need in order to calculate their predicted times, and they'll be able to predict that within maximum error 8.4% error rate. And so returning back to their original question that motivated the group to create this new IO-aware model, are they able to predict the runtimes with different IO speeds? And is it true that IO is no longer a bottleneck within the Apache Spark framework? And what they found was that no, IO is still playing an important role in the runtime for these large data processing applications. And from their results, this shows, since they were able to switch to SSDs to not only improve the runtime, but also decrease the cost for running an application on a public cloud server.
Okay. So in terms of related works to this type of optimization and modeling for large big data applications such as Spark or MapReduce, there's this paper by Ousterhout et al. Entitled Making Sense of Performance in Data Analytics Frameworks, in which that research group utilized block time analysis to study the impact of network and IO operations in Spark. And the interesting thing that they were able to derive from their research is that network operations for Spark-based applications were far more impactful than IO-based operations. For example, the moving from 1 gigabit per second to 10 gigabit per second in terms of your network bandwidth would be far more impactful than increasing your IO access times, simply because most of the time spent blocked on the network outweighs the time spent blocked on the disk. And from their optimization model, they found that optimization on network storage would be capable of reducing runtime by about 19%. And they found that IO was not a bottleneck for Spark applications as a result, since the network, the effects of network bandwidth were far more impactful. And then a separate related work, a group Gianetti et al. Published a paper entitled Fluid Petri Nets for the Performance Evaluation of MapReduce and Spark Applications, in which they utilize Petri nets to model performance of MapReduce and Spark applications. This research group focused mostly on single user-shared clusters, resulting in a far more limited model than the research group that we were talking about in our presentation. They found that their model predicts application time with an average accuracy of about 9.5% for MapReduce-based applications and 10% for Spark-based applications. And their model ended up being validated by Seneca, the Italian Supercomputing Center, and Microsoft Azure, which allowed for far more in-depth testing and verification on their models, since they had a lot more resources dedicated towards independent testing, which is a plus for this type of paper.
And so overall, for our thoughts on this paper, we think it makes a really good argument into why I/O is still a very important area of development and why there's still a lot of room for in-memory computing designs to be implemented and to help improve the performance of running large-scale data applications and to help lower the cost of running them on these large-scale public clouds. We also like how the model developed by the research group uses input arguments that are not application specific. So they started off talking about the GATK4 application a lot and focusing all of their analysis in that, but their end model used only used inputs such as data access size, number of tasks, and execution times, which are at a level of abstraction high enough to flexibly use in other frameworks. We noticed that the group didn't test their model against systems that didn't have the 1 master and 10 slave nodes design. And so we think that there'd be room to maybe analyze how changing the number of masters and slaves in a distributed system would impact their model's predictions. And so these are the references we used to do our research. Thank you again for listening.